Chapter 11, Section 3 begins with changes of state. During a state change, such as going from solid to liquid or liquid to gas, entropy and enthalpy are going to change dramatically. So that's when their biggest changes occur. Heat of fusion is represented by delta H and then FUS as a subscript. That means that's the heat absorbed when 1 mole of a substance melts. It's also referred to as the molar enthalpy of fusion. Now the opposite state change would be then vaporization. So the heat of vaporization or molar enthalpy of vaporization is symbolized by delta H with VAP as the subscript, and that's the heat that's absorbed when 1 mole of a liquid turns into a gas or a vapor. So fusion is referring to melting, vaporization is referring to going from a liquid to a gas. I expect you to be able to interpret a graph similar to these items here. This one is plotting temperature versus enthalpy, and this just points out where those big jumps in enthalpy are. So here you would have a solid, something in the solid state of matter at low temperatures, low enthalpy, and when it reaches the point where it's going to melt, go from the solid to the liquid state, that's where we're going to have our delta H of fusion. So there's a big jump right here. Then, once you have a liquid, you'll continue heating that liquid, enthalpy will continue to rise, and then you'll eventually reach the melting or the boiling point, which is where your liquid is going to turn into a gas. And so this big jump here is the delta H of vaporization, or molar enthalpy of vaporization. And then finally, once you're in the gas state, the rest of this graph is just showing if you continue increasing the temperature, the enthalpy will continue increasing as well. But the main ingredients here are when you have these big jumps, those are your changes in enthalpy for fusion and vaporization. Gibbs energy, or Gibbs free energy, is represented by a capital G, and that's going to determine whether a reaction is spontaneous or not. The units are generally in kilojoules or joules, sometimes kilojoules per mole. And basically, spontaneous reactions are ones that occur without any outside assistance. They already have enough energy present. And non-spontaneous energy or reactions need energy added in. So if your delta G, or change in Gibbs free energy, is negative, that means that the reaction is spontaneous. So you don't have to add in any energy. If your delta G is positive, that means it's non-spontaneous and you would have to add in energy in order to make the reaction occur. Our equation that we'll be using for Gibbs free energy is delta G is equal to delta H minus T delta S. So delta H is our enthalpy change, temperature is, T is temperature, and this time it has to be in Kelvin. You do need to convert it if given Celsius. And then delta S is the entropy. So here's a sample Gibbs problem. This one says if the delta H is 41.2 kilojoules per mole and delta S is 0.0418 kilojoules per Kelvin, is the following reaction spontaneous at 25 degrees Celsius? So generally these reactions will just, or these problems will just ask us if the reaction is spontaneous or not. They won't say necessarily to calculate Gibbs free energy, so you will need to know that. So we want to list out our equation, substitute, and solve. So our equation is delta G equals delta H minus T delta S, and then we plug in our values. We're given delta H. The temperature is listed as 25 degrees Celsius, so we add 273 to get Kelvin, and our delta S was 0.0418. So when we add that into our calculator, we get a value of 28.7 kilojoules. And since it is a positive value, then that means that this reaction is non-spontaneous. So we would have to add in 28.7 kilojoules of energy to make this reaction happen.